This video is for Section 8.3, Estimating a Population Mean. So we are going to be doing a one sample Z interval for a population mean. So you have been doing population proportion, and now we're going to move on basically to the average of that population. So we're going to draw a simple random sample of size n from a population having unknown mean mu and known standard deviation sigma. As long as the normal and independent conditions are met, a level C confidence interval for mu is x bar plus or minus z star times sigma over the square root of n. The critical value z star is found from the standard normal distribution. Choosing sample size for a desired margin of error when estimating mu. To determine the sample size n that will yield a level C confidence interval for a population mean with a specified margin of error ME, you have to get a reasonable value for the population standard deviation sigma from an earlier or pilot study, find the critical value Z star from the standard normal curve for confidence level C, set the expression for the margin of error to be less than or equal to the margin of error, and solve for n. So you're going to be using Z star times sigma over square root of n less than or equal to the margin of error. So we're going to look at an example that has to do with determining sample size for margin error. So it says, researchers would like to estimate the mean cholesterol level mu for a particular variety of monkey that is often used in laboratory experiments. They would like their estimate to be within 1 milligram per deciliter of the true value of mu at a 95% confidence level. A previous study involving this variety of monkeys suggests that the standard deviation of cholesterol level is about 5 milligrams per deciliter. The problem we have to solve is obtaining monkeys is time-consuming and expensive, so the researchers want to know the minimum number of monkeys they will need to generate a satisfactory estimate. Alright, so we are going to be using the Z star times sigma over the square root of n has to be less than or equal to the margin of error. We are doing this for a 95% confidence level. And remember, when we do a 95% confidence level, our Z star would be equal to 1.96. If you remember or don't remember how to do that, remember you can do inverse norm. 95% confidence means that you would have 5% that was not covered underneath your standard normal curve. And so you would split that between your two tails that you have here. So each tail would be 2.5%. So the area that you would be looking for would be the 95% here plus this 2.5 here. So 95% in the middle, and then this 2.5% here. So really you are looking at 0.975. I got that from saying 0.95 plus the 0.25. 0.025, excuse me. And so then because you're using a standard normal curve, your mean would be 0 and your standard deviation would be 1. And you could go to your calculator and go to second bars. Option 3, you're going to do 0.975, mean of 0, standard deviation of 1. And whenever you do that, you would get 1.959963986, but that would round, of course, to 1.96. Remember, anytime you're using a 95% confidence level, your Z star that corresponds with that is always going to be 1.96. So, you also know that your sigma, it tells you, is 5 because it came from a previous study. And you know that your margin of error that they want you to use would be at most 1. And the reason I know it's at most 1 is because I want it to be within 1 milligram per deciliter. That was a very pitiful line, but you get the idea. So it's got to be, that's what tells me what I want my margin of error to be. So then I'm just going to fill in what I know into this formula. So I'm going to say 1.96 times 5 over the square root of n, because that's what I'm trying to figure out. And then it has to be less than or equal to 1. So what I can do now is basically just solve for n. So I'm going to divide everything by 1.96. Whenever I do that, I would get 5 over the square root of n less than or equal to. If I do 1 divided by 1.96, I would get 0.51. We'll go with 0.51. I'm going to multiply everything by the square root of n so that I can get rid of that fraction. When I do that, that cancels. I'm going to have 5 less than or equal to 0.51 square root of n. I'm going to divide everything by 0.51. That cancels. Then I would do 5 divided by 0.51. And I would get 9.80 less than or equal to the square root of n. I'm going to square both sides so that I can get rid of my square root. So then I'm going to say 9.8 squared, which gives me 96.04 less than or equal to n. Alright, so remember that your n in this case is representing monkeys. So you want to make sure that you actually round up on this one. So anything that's over 96 would count as 97. So you would actually need 97 monkeys, because thankfully we can't have 4/100ths of a monkey. All right, check your understanding. To assess the accuracy of a laboratory scale, a standard weight known to weigh 10 grams is weighed repeatedly. The scale ratings are normally distributed with unknown mean. This mean is 10 grams if the scale has no bias. In the previous study, the standard deviation of the scale ratings has been about 0.0002 grams. How many measurements must be averaged to get a margin of error of 0.0001 with 98% confidence? Show your work. So again, you're using z star times sigma over square root of n. It has to be less than or equal to your margin of error. So we want to start with figuring out what our z star is. So we're doing a 98% confidence, which is going to turn into our z star. To do that, remember you have your curve. The 98% would be the 98% that's contained in the middle, which is going to leave us with 2% that's left over, which means each one of the tails is 1%. So when I go to do this on the calculator to find my z star, I'm going to do inverse normal, but I'm going to say 0.98 plus 0.01. So I'm really going to say 0.99. My mean would be 0 and my standard deviation would be 1 because it does tell me it's normally distributed. So then I'm going to do second vars 3.99. Everything else stays. That gives me a z star of 2.326. 2.326. So my Z star is this 2.326. All right, sigma, it tells me, is 0.0002, and that came from right here, the standard deviation. Scale ratings has been 0.002 grams in previous studies. It also tells me that for my margin of error, I want to get 0.0001. So all I'm going to do now is just plug into this formula. So I'm going to say 2.326 times 0.0002 over the square root of n. We want it to be less than or equal to 0.0001. So I'm going to start by getting rid of anything that's on this side that's not part of the part that's got the n in it. So I'm going to divide by 2.326. So that's going to cancel. I'm going to get 0.0002 over the square root of n less than or equal to, on my calculator, 0.0001 divided by 2.326 gives me 4.299. Let's go ahead and round that up to 4.3. Multiply both sides by the square root of n so that I can get rid of the fraction. So I get 0.0002 less than or equal to 4.3 times the square root of n. Now I'm going to get the square root of n to be by itself by dividing by 4.3. So 0.0002 divide by 4.3. So 4.65 less than or equal to square root of n. Square both sides. So 4.65 squared gives me 21.6225. Less than or equal to n. Of course, we would need to round that up, so we would really need 22. Because we're talking about measurements, and of course it would be kind of difficult to get 0.6225 of a measurement. So 22 measurements. The T distributions, degrees of freedom. So we're going to draw a simple random sample of size n from a large population that has a normal distribution with mean mu and standard deviation sigma. The statistic t is equal to x bar minus the mean mu over the standard deviation of x over square root of n. Has a t distribution with degrees of freedom, which we represent df to equal n minus 1. This statistic will have approximately a t sub n minus 1 distribution as long as the sampling distribution of x bar is close to normal. Alright, so for this check your understanding section, it says to use table B to find the critical value T star that you would use for a confidence interval for a population mean mu in each of the following situations. If possible, check your answer with technology. I'm going to show you how to use the technology, and then we can talk about table B later on, like in class sometime. You're going to have the calculator. Table B is kind of like the standard normal table. You guys end up just using the calculator for that anyway, so I'm going to show you how to do the calculator, and then we can talk about that later if you want to. Alright, so we're going to find, our goal is to find the critical value T star. Now, whenever you are finding a T star, you can do that on the calculator by using the inverse T. Actually, I think it's a capital T. So the inverse T on your calculator. So for A, you want to do a 98% confidence interval based on n equals 22 observations. So we're going to go on the calculator to second vars, and you're going to go to option 4. So you're used to using inverse normal, you use that a good bit, but now you're going to go to inverse T. So you do inverse T. Your area that you are going to use is going to have to do with your confidence interval. So you're going to say, okay, if it's 98%, that means 98% is in the middle, which means that each of the tails added together is the extra 2%, which means this one is 1%. So that means that my confidence interval, or my confidence level, for 98% means that I'm actually going to use 0.99. And the reason I'm using 0.99 is because I'm trying to find the area underneath that curve from this dark line on. And so I'm doing all the 98% and then the extra 1%. So 0.98 plus 0.01, which then gives us 0.99. So the area underneath the curve that we're looking at is 0.99. Then it asks us for degrees of freedom. So our degrees of freedom for this one would be n minus 1. Actually, always df, or degrees of freedom, is n minus 1. So our n is 22, which means our degrees of freedom would be 22 minus 1, which is 21. So then on our calculator, df would be 0.21. And then you go paste. Well, this is unfortunate. That's why. 0.21. Nope, not 0.21. Regular 21. Alright, so then that's what we should get. Boom. Okay, so our answer is going to be 2.517647992. So our T star, then we would say, we'll round that to 2.518. B. For B, it says a 90% confidence interval from a simple random sample of 10 observations. So our confidence that we're looking at is 90%. So 90%, of course, standard normal, in the middle, 90%, which means that there's 10% left over in the tails, so each tail is 5%. So then I'm going to be looking at the area underneath this line, which would be the 90% plus the 5%, so 0.90 plus 0.05, 0.95. So I'm really looking at 0.95. My degrees of freedom I can always get by saying n minus 1. And so for this one, it tells us a simple random sample of 10 observations, so our n is 10. So 10 minus 1 would be 9. So we go to the calculator, we go to second vars, we go to 3. Our area is 0.95. Oh, I lied, not 3. Second vars, 4. So I'm so used to going to 3. 0.95 degrees of freedom was 9. Paste. So we get an answer that is 1.833. So our T star is 1.833. For C, we're finding a 95% confidence interval from a sample of size n. So our confidence is 95%, which means that underneath the standard normal curve, the 95 would be in the middle. 5% is left over in the two tails, which means each tail is 2.5%. So our 95% confidence is going to turn into 0.975 underneath that line. So everything to the left of that line. Our degrees of freedom we would get by saying n minus 1. So our n is 7. 7 minus 1 gives us 6. We go to the calculator and do second bars. We do option 4 because it's inverse of t, and that gives us our t star. 0.975 would be the area underneath the curve that we were looking at. Our degrees of freedom would be 6. And then we paste and get our t star is 2.4469. So t star is 2.447. Alright, so next we're going to talk about standard error of the sample mean. The standard error of the sample mean, x bar, is standard deviation x over square root of n, where standard deviation of x is the sample standard deviation. It describes how far x bar will be from mu on average in repeated simple random samples of size n. It goes on to say the one sample t interval for a population mean, we're going to choose a simple random sample of size n from a population having unknown mu. A level C confidence interval for mu is x bar plus or minus c star times standard deviation of x over square root of n, where t star is critical value for t sub n minus 1 distribution. Use this interval only when 1. The population distribution is normal, or the sample size is large, which means that you are taking more than 30. And 2, the population is at least 10 times as large as the sample. So, conditions for inference about a population mean. And so you are going to have to look at random, normal, and independent, just like you did earlier on in this chapter. To be random, the data must come from a simple random sample of size n from a population of interest or a randomized experiment. This condition is very important, so it has to be random. The second is normal, so the population has a normal distribution or the sample size is large, which means that your n is greater than or equal to 30. And the third thing is that it's independent. So the method for calculating a confidence interval assumes that individual observations are independent. To keep the calculations reasonably accurate, when we sample without replacement from a finite population, we should check the 10% condition and verify that the sample size is no more than 1/10 of the population size. So, we are going to look at an example of constructing a confidence interval for mean. A manufacturer of high-resolution video terminals must control the tension on the mesh of fine wires that lies behind the surface of the viewing screen. Too much tension will tear the mesh and too little will allow wrinkles. The tension is measured by an electrical device with output readings in millivolts. Some variation is inherent in the production process. Here are the tension readings from a random sample of 20 screens from a single day's production. Construct and interpret a 90% confidence interval for the mean tension mu of all the screens produced on this day. we want to estimate the true mean tension mu for all the video terminals produced this day at a 90% confidence level. So we are going to first check to make sure that all the conditions are met. So we're going to make sure it's random. And so in our problem, it told us that the data comes from a random sample of 20 screens from the population of all the screens produced that day. So it's definitely random. Alright, so next we need to check and make sure that it's normal. So we have two conditions that we can look at for normal. So we either look at n, our sample size, and we make sure that it is greater than or equal to 30, which in this case it's 20. So we have to look at the second condition that we can meet to be normal. And that's just basically that it is normal. So it doesn't have anything that seems to be kind of strange. Now you could look at the graphs. So you could look at the dot plot or the box plot. And basically you are just looking to see that you are not strongly skewed in any way or that you don't have any outliers. And so we can kind of go through this and see that all of our numbers seem to be relatively close together. They don't seem to be like one's way far out. It doesn't seem like it's kind of heavy on one side or the other. They seem to be pretty balanced, so we can say that this one is normal. I encourage you to feel free to graph these either with a box plot or with a dot plot so that you can compare those. For lack of time and because it's kind of a time-consuming process, I'm not going to go through that on the video. You are very familiar with how to create a box plot and how to create a dot plot. The last thing that you have to check is you have to make sure that it is independent. And basically we are taking these screens and we are getting one reading from the screen. And so because we are sampling without replacement, we must check the 10% condition and make sure that that is met. And so basically we are doing 10 times our number in the sample, which is 20. And so that gives us 200. And so is it reasonable to think that there were 200 TV screens that were, or whatever this is, that were created in that day? And it's probably reasonable to assume that there were that many created in that day. So this works as well. Alright, so the next thing we have to do is to find the mean and the standard deviation for the 20 screens in the sample. And so to find our mean, which is x bar, we can go on the calculator, and I've already typed these into L1, so they should already be in the calculator. Stat, edit, L1, so all of the readings are in there. So then I can go to second vars. Actually, no, I can go to stat. So it's in stat, it's over in calc, and we're going to do one var stats. So one more time. Go to stat, edit, everything in the list. Then you go to stat again, go over to calc, and you're going to go to one var stats, and that will calculate your x bar for you. So then I'm going to go to calculator, and x bar is 306.32, and that is in millivolts. Alright, the next thing that I have to do is I have to get my standard deviation. So I can also get that from on the calculator. So on the calculator, standard deviation 36.21, we'll say. And that was also in millivolts. Alright, so we are going to also have to have our degrees of freedom for this. And so that's n minus 1. N, of course, was 20. So 20 minus 1 gives us 19 for our degrees of freedom. And it tells us that we are using a 90% confidence interval. So our confidence is 90%. And to find out the T-star that goes along with that, we would need to do the inverse T. The area that we would be looking at, keep in mind, 90% is in the middle, which means 10% is not taken care of. So this is another 5%. We're looking at everything to the left of that line right there. So we're looking at an area of 0.95. Our degrees of freedom we already said was 19. So we go on our calculator to second bars. We do option 4 because it's inverse T. Our area is 0.95. And our degrees of freedom is 19. And that will give us our T-star, which is 1.729. All right, so to put all of that together, we're going to use our formula x bar plus or minus T star times the standard deviation of x. I'm really trying to make that happen. That's not going to happen for me. Over the square root of n. So that's going to look like 306.32 plus or minus 1.729 times 36.21 all over the square root of 20. So then you can go to the calculator and you can type everything in. So we'll do 2 different times, one where we have plus and one where we have a minus. So we'll do 306.32 plus 1.729 times alpha y equals to get the fraction. On the top, 36.21. On the bottom, square root 20. This will give us our upper, which in this case will be 320.32. All right, to get the lower, we're going to do the same thing. So I'm just going to copy this. And the only thing that I'm going to change is that plus sign that's right there. And I'm going to change it to a minus, and it will give me lower. Oh my gosh, this is so slow. It actually is painful. All right, so then that gives me 292.32. So what that means is we just found a one sample t interval to estimate what the mean was. And so that interval would be between 292.32 and 320.32. The last thing we have to do is conclude what that means. And so remember, when we conclude on these where we're talking about confidence interval, we're actually going to write out what it actually means. So we're going to say we are 90% confident that the interval 292.32 to 320.32 millivolts captures the true mean tension in the entire batch of video terminals produced that day. All right, so I also have good news. In place of doing all this work that we did here, there is a way that you can do this on the calculator so that it saves you a little bit of time. Remember, it's always good for you to know what these formulas are so that you can show off what you know on the AP exam. The way that you would do this one is you would go in your calculator. You are going to go under stats, or stat, go over to tests, and you are going to do a T interval, which is option 8. You are going to keep it on data. You're going to change your confidence level to 0.9. You're going to make sure that you leave your L1, so your stat L1 that you did earlier, you're going to keep that, so your list should show L1. Keep your frequency at 1, and then you're going to go to calculate. Whenever you do that, you get the same thing we did, but in a lot shorter time, and it also gives you the X-bar and the standard deviation so that you don't have to work those out doing it either by hand or on the calculator in the 1-bar stats. All right, so check your understanding. Biologists studying the healing of skin wounds measured the rate at which new cells closed a cut made in the skin of an anesthetized newt. This means they got anesthesia. Here are the data from the random sample of 18 newts measured in micrometers, millionths of a meter per hour. And so then you have this data set here. So we want to estimate the mean healing rate mu with a 95% confidence interval. The first thing it says is define the parameter of interest. So what you are trying to find, I'm going to type this out because my handwriting's not great on here. So what you are trying to find is the population mean healing rate. The second thing that you are doing, it says what inference method will you use? And then check the conditions for using this procedure are met. So for this, you would need to calculate a 1 sample T interval for mu. So to check that, you would have to do, is it random? You would have to check and see if it's normal. And you would have to check and see if it is independent. So it tells us it's a random sample, so that's good. All right, so then to check and see if it's normal, you can either see if you have a sample size that's bigger than 30, and so this is 18, definitely not bigger than 30, so we have to go to the second one, which is just basically seeing if we think that the graph is normal. So basically, do we have anything that seems to be like super way off, or anything that seems to be like an outlier or makes the graph kind of seem swayed in one direction or the other? All of our numbers seem to be fairly close together. They also all seem to be reasonable. Nothing seems to be really, if we were to look at this, nothing seems to be really pulled out in one direction. So we'll say that this is normal. Like I said before, always welcome to use a dot plot or a histogram or a bar graph so that you can kind of see, or a box plot, see what you've got going on. You are familiar with how to do all those, so I'm not going to cover that in this video. All right, the next thing you have to do is to check and see if it's independent. So you have data on 18 of the newts. There are clearly more than 180 newts based on the 10% condition. So 10 times 18 would give you 180. So you need to make sure that in all over the place, there would be more than 180. And so there definitely would be more than 180 newts if you were talking about ever. So that means that independent is met as well. All right, so then we're going to move to 3, which is to construct a 95% confidence interval for mu. So our confidence is going to be 95%. So one way that we can do this is by hand, like I did in the last example, but I'm going to show you how to do it on the calculator so you see a fresh calculator example. So what you want to do first is make sure that all of your sample is listed in L1. So I have already done that, and L1 should be all the numbers from our sample. So then you're going to go to Stat, you're going to go over to Tests, and you're going to do a T interval. So 8. Keep it on data, keep it on L1. We're going to change our confidence level to 0.95 and then calculate. So whenever we do that, we get an interval 21.53 to 29.81. And then for 4, it says interpret your interval in context. So I'm going to type that one out. So we're going to say we are 95% confident that the interval from 21.53 to to 29.81 captures the true mean healing time for newts. All right, next we're going to talk about robust procedures. So an inference procedure is called robust if the probability calculations involved in that procedure remain fairly accurate when a condition for using the procedure is violated. So for using one sample T procedures, the normal condition. So your sample size has to be less than 15. So you're going to use T procedures if the data appear close to normal, roughly symmetric, single peaked, no outliers, all that good stuff. If the data are clearly skewed or if outliers are present, do not use T. So if your sample size is at least 15, the T procedures can be used except in the presence of outliers or strong skewedness. And if you have large samples, the T procedures can be used even for clearly skewed distributions when the sample is large, roughly n is greater than or equal to 30.